The average weight of women in the United States is 164.7 pounds. These weights are normally distributed with a standard deviation of 37.5 pounds. If one woman is randomly selected from the U.S. population, what is the probability that she weighs between 175 pounds and 195 pounds? Okay, so it says they're normally distributed, right? The weights are normally distributed, so we can go ahead and draw a bell curve as a visual aid. And then we'll locate the center of the bell curve at 0 for the z number line. And for the x number line, which is going to correspond to weights, we'll write it in as 164.7, which is the mean, right? According to the problem. We also want to record the standard deviation, so we'll write that over here just so we have it at our fingertips when we need it. And from there, we want to put the two numbers of interest on our drawing. It says that we're looking for the probability the woman that we randomly select weighs between 175. Now 175 is on the upper end of the curve because it's above average, and 195, that's also on the upper end of the curve, right? So we're looking for the area between 2 points that are on the same side of the curve, in this case above average, right? So we'll shade this area because that's the area we're looking for, the area between these two numbers they gave us. And then we'll need to convert them into z-scores. So to convert 195 into a z-score, it'll be z is equal to 195 minus 164.7 divided by that standard deviation of 37.5. To do the same for 175, it'll be z is equal to 175 minus the mean of 164.7 over the 37.5, right? Same standard deviation. Now I've already done the 175 in previous videos, so I'm just going to pop that up and show you that. So just 175 minus the mean divided by the standard deviation. Press enter and you get 0.27 as a decimal. So 0.27, that's rounded off to 2 decimal places. Remember, z-scores should be rounded off to 2 decimal places after the decimal point. Now I'm going to do the same for 195. Basically, I can just recall that computation and change the 175 into a 195. When I do that, I get 0.808. Rounding it off to 2 decimal places, I'll get 0.81. 0.81. All right, now, if I look up 0.27, I'll get the area from here to here, which is not the area I want, right? It's none of the area I want, in fact. If I look up the 0.81, I'm going to get this area from here to here, right? Which is all of the shaded region, and that's the area I want, but it also gives me the part that I don't want. So the logic here again is to subtract these two answers from the z-table so that we end up with just the area we want, right? Because if I take from the larger area this smaller area that I'm not interested in, I will be left with exactly the part that I am interested in. So let's go look up 0.81 first and see what that gives us. So here's 0.8, right? And then 0.80, 0.81. So I'm looking at 0.2910 for the 0.81 value. So 29.10. So 0.2910. And again, I've written it so it overlaps both the white part and the shaded part. And this way I'm aware that that's not the area I want precisely. It's got extra area that I'm not interested in. So let's look up the 0.27, see what that gives us. So here's 0.2 again, and then 0.27 will be over here. So 0.1064, 0.1064. And to get the final area that I'm interested in, I will just simply subtract, right? So I have to subtract these two answers. In other words, I'm going to do 0.2910 minus 0.1064, and that will leave me with the area I'm interested in. Just to make it faster, we'll go ahead and do that in our calculator. 0.291 minus 0.1064. And we get the answer 0.1846, or 18.46%. All right, so remember in this problem we used the idea of same side subtract. Since we're looking for the area between two values that were on the same side of the curve, we subtracted the table values that we got.